Back in Notes 10, we introduced the ideas of momentum and impulse and center of mass. So now for Notes 11, we're going to kind of bring all that together and look at conservation of momentum. So as I'm going through these notes, rather than writing out each thing's in the blanks, because it's kind of small to write on my tablet, I'm just going to circle the blank or put a line through it or something as I say what goes in the blank, so that hopefully you can just record it in your notes based on what I'm saying in the video. So, for conservation of momentum, in any situation, the total energy is always conserved. Because energy cannot be created or destroyed, you can only convert it from one form into another. So total energy is always conserved, no matter what. However, in things like explosions, in which one object separates into two or more objects, or in collisions, in which you have two or more objects coming into contact with each other, the mechanical energy, which is the stuff that we can calculate, is usually not conserved, since other forms of energy are generated, such as sound and thermal energy. You've seen in the past that every time we have some kind of explosion or collision, the sound and thermal energy are generated, and because those are not forms of the mechanical energy, which are kinetic and potential, we cannot incorporate those into the calculations. So, when these collisions or explosions happen, and even though the total energy is conserved, we cannot analyze them in terms of the energy, so we have to then analyze them using momentum instead. So conservation of momentum states that the total momentum of a system of objects during an explosion or a collision remains constant, provided that no net external force acts on the system. So the way we're going to write this is given in the first box below. So I'm going to take that, just so you can see it, and extend it over to here. In that first box would be the initial momentum, and where momentum was abbreviated with the letter P, and it's a vector, is simply equal to the final momentum, P final. If two objects collide, but they don't stick together, then we can take that conservation momentum equation and we can write it as shown in, and I'll take the second box and write it up here. We have two objects, each has a momentum of mv, so I'm going to call it m1 v1 for object 1 plus m2 v2 for object 2. That's the initial momentum of object 1 plus the initial momentum of object 2 is equal to the final momentum of object 1, m1v1, plus the final momentum of object 2, m2v2. But the issue with how this is written right now is it doesn't differentiate between the initial and the final velocities. So on every velocity, because velocities are the things that change, not the mass, I also need to write whether it's an initial velocity, using an I on the left side of the equation, or a final velocity, using an F on the right side of the equation. And then all those velocities are vectors. So this is what this equation will become if the two objects collide but don't stick together. You have two separate objects, this one and this one. They collide, and that gives two separate objects after the collision. This one and this one. Now the other common case is if the two objects stick together after the collision. If there's some way that they kind of couple together and don't come apart, then the conservation of momentum equation is given what's in this third box, which is, now the left side of the equation stays the same. You have two objects that are separate, m1 v1 initial plus m2 v2 initial, both those velocities are vectors, is equal to, now the final momentum, since the two objects are joined together now as one object, we're only going to have one term on the left side. The total mass of that object is going to be a combined m1 plus m2, which we're going to put in parentheses. And the two objects, because they're stuck together, are going to have the same final velocity. So rather than calling it v1f or v2f, we'll just call it vf. That's a joint final velocity between both the objects. And this is the equation you want to use if two objects get stuck together. You have object 1 plus object 2, which are separate initially before the collision, and that becomes one single object with a mass m1 plus m2 times its joint velocity, vf, is the final part after the collision happens. So let's look at this collision example. You got a 1,500 kilogram car moving to the right with a speed of 30 meters per second, and it collides with a 2,500 kilogram truck and locks bumpers with it. So we want to calculate the velocity of the two vehicle combination after the collision for each of the following situations. And what you should notice on here is that the part it says where it locks bumpers, because that means for all three of these cases we're going to be using this equation where the two objects stick together after the collision. So let's do part A up here. And in part A, the car hits the truck, which is initially stopped at a red light. So if I write out the equation, m1 v1 initial plus m2 v2 initial is equal to m1 plus m2 v final, we want to do the same thing here that we did back when we started looking at conservation of energy, which is first check to see if any of the terms go to 0, and if they do, just get rid of them. Well, m1 refers to the car, and m2 refers to the truck. And it says the car was initially moving, so we know that the term on the left side, the m1 v1 initial, is not going to be 0, but that second term, the m2 v2 initial, will be 0, because it says the truck is initially not moving. It was stopped at a red light. So with that term going to 0, we can now solve this equation for the vf. So just divide both sides by m1 plus m2. And when you divide the right side by m1 plus m2, that part will cancel out. So the final velocity of the combination is just equal to m1, mass of the car, which is 1,500, times its initial velocity, which was 30, divided by m1 plus m2, so 1,500 mass of the car plus 2,500 mass of the truck is 4,000. And this is equal to 1,500 times 30, which is a 45, followed by 3 zeros, divided by 4,000, which also has 3 zeros. So with the zeros canceling out, you're left with 45 divided by 4, which gives you a final speed of 11.25 meters per second. So the car and the truck are now moving together with a speed of 11.25 meters per second. Alright, let's do part B. This time, the car rear ends the truck, which is traveling at 20 meters per second in the same direction as the car. So we're going to start this one the same way, which is m1 v1 initial plus m2 v2 initial equals m1 plus m2 times v final the major difference here is that since the truck was not initially stationary, we could not set this term, the one we set before, equal to 0. That term is no longer 0. So nothing in this equation will go to 0, so we just have to divide both sides by the m1 plus the m2, so that it cancels out, and then we can just plug in for VF. So we have 1500 times 30 plus, now the truck is 2500, and that was moving at 20 meters per second, divided by the sum of the car and the truck's mass, which was 4,000. And what we're left with here is 45,000 for the car, plus, now you've got 2,500 times 20, which is 50,000 for the truck, divided by 4,000. We have 95,000 divided by 4,000, which simplifies to 95 divided by 4, and you get an answer of 23.75 meters per second. And this answer should make sense, because if the car was originally going at 30 meters per second, when it hits the truck, it's got to slow down the car. And if the truck is going at 20 meters per second, when something hits it from behind, it's going to speed up a little bit. So the final answer has to be somewhere between 20 and 30 meters per second. And that's what we got with our answer of 23.75 meters per second. So part C, this time the car collides head-on with the truck, which was traveling in the opposite direction at 20 meters per second. So we actually start this problem off the exact same way. In fact, I don't even need to rewrite anything, because the equation, because they're still locking bumpers, it's still going to be the exact same equation, and nothing went to 0. So everything is exactly identical to what it was up here. The only slight difference now is what we're going to be plugging in as the numbers, because the one difference is that the truck is traveling in the opposite direction. And one of the things you have to remember about momentum, and I mentioned this as a really important note in the previous set of notes that people always forget to do, is that when something's traveling in the opposite direction, because momentum's a vector, you have to make it a negative number. So this 20 meters per second right here is the speed of the truck, but the actual velocity of the truck is going to be negative 20 meters per second. So when we go through all this stuff and we get down to our final equation, which is the 45,000 plus, it turns out that this part right here, the 2,500 times 20, is going to be 2,500 times negative 20, which gives you a negative 50,000. When you divide that by 4,000, so you get 45,000 minus 50,000, which is negative 5,000, and negative 5,000 divided by 4,000 is the same as 5 divided by 4, or negative 5 divided by 4, which is negative 1.25 meters per second. And this should make sense, because if the two vehicles are traveling in opposite directions toward each other with almost the same momentum, one has 45,000 and one has 50,000, but negative, when they actually join and lock bumpers, they're barely going to be moving at all. The truck had slightly more momentum than the car, and it was traveling in the negative direction, which is why the final answer came out to be negative. Okay, so moving on. Another common thing where momentum is used is whenever a firearm is discharged, the firearm jerks backward in what is known as recoil. This is simply due to the conservation of momentum, which we're going to illustrate in this example. It says determine the recoil speed of a 1.2 kilogram pistol that shoots a 20-gram bullet at 300 meters per second. So, if I write out the conservation of momentum equation, the P initial is equal to P final. Let's break this down in terms of the gun and the bullet. So I can just write down M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. Well, let's say M1 is the gun and M2 is the bullet. So initially, when you're just holding the gun with the bullet inside it, neither of them are moving. So technically what that means is that this term goes to 0 and this term also goes to 0. The initial momentum of the whole thing is 0. Well, now how is that possible? Because after what this is considered an explosion, because two objects are separating, after the explosion, both objects are moving. But what happens is, with the bullet moving in one direction, which is positive, that's going to cause the gun to recoil, which means it's moving in the opposite direction. It's going backwards with a negative velocity. And that's what you're solving for. So, we can just write this. We are solving for the final velocity of the gun, which we said was V2 final. So, if we just take this equation to get V2F by itself, I'm going to bring this first term over to that side. So we have negative M1 V1 final is equal to M2 V2 final, and then just divide both sides by M2. So this is a really simple example of conservation of momentum, because when the M2s cancel out, we're left with negative M1, the mass of the bullet, 20 grams. Bullets are usually measured in grams, and you have to remember to convert them into kilograms. So 20 grams is 0.02 kilograms times its velocity of 300, and that's divided by M2, the mass of the pistol. And when you divide the numerator, which is 6, by 1.2, you get an answer of 5. Remember, it was negative because it's recoiling. It's going in the opposite direction. So negative 5 meters per second. Technically, because it's asking for speed, you would ignore the negative sign, because the negative 5 meters per second is the velocity, but the recoil speed is just the magnitude of it, the 5 meters per second. Alright, so that's all for that example. And the final thing on the front of this page just says, in some cases, collisions are 2 or 3 dimensional. Doesn't really come up that much. But for these cases, for the cases with the 2 or 3 dimensions happening, the initial and final momentum of each object must be broken into components. The initial and final momentum of each object must be broken into components, like an x component and a y component, and the momentum must be conserved in each direction. So you've got to conserve the momentum in the x direction, and then you've got to conserve the momentum in the y direction. Okay, on the back of the page, the impulse momentum theorem states that the total momentum of a system of objects changes if an impulse acts on the system. You may remember from the last set of notes that we defined impulse, which is a capital J, equal to force times time, which is also equal to the change in momentum. So if we write out the change in momentum, the delta P, as the final momentum minus the initial momentum, and just keep that as equal to F times T, what this is saying is that the impulse momentum theorem, the impulse, which is this first term, is equal to the change in momentum, this last part. So if I bring this Pi, the initial momentum, over to this side of the equation, what you can write in the box here is the initial momentum, Pi, plus the impulse, which is F times T, will result in a different final momentum. And that's the impulse momentum theorem. The initial momentum plus the impulse, F times T, equals a new or different final momentum. If the impulse acts in the same direction as the initial velocity, the momentum will increase. Which is saying if an object is moving in a certain direction, and then you apply an impulse or a force to it in that same direction, it's just going to cause it to increase its momentum. But if the impulse acts in the opposite direction as the initial velocity, the impulse will decrease, because you're causing it to slow down. Or, if you have the force hard enough, it'll cause it to decrease so much that it ends up stopping it completely and causing it to go in the other direction. So the momentum will either decrease or change direction. And this last part of the notes, the types of collisions. You've seen this before because when we did the lab with the 3 different collisions during class, we saw 3 different types of collisions, which are outlined right here. So, in any type of collision, the total energy, remember this is all the energies, not just mechanical energy, but the total energy and the total momentum of the system are always conserved. However, as we said before, this does not necessarily mean that the mechanical energy is conserved. So we're going to categorize collisions by what happens to the mechanical energy, but more specifically, because collisions will really just change the velocities of the objects and not really the heights of anything. If you're looking at the momentary time a collision happens, we don't even care about the gravitational energy, we only care about the kinetic energy. So collisions are categorized according to what happens to the kinetic energy. So the first type, an elastic collision, is one in which the kinetic energy is conserved. i.e., or in other words, Ki equals Kf. That goes in that second blank right there. You can just say kinetic energy is conserved. Ki is equal to Kf. Sometimes you may see this referred to or called a perfectly elastic collision, with the word perfectly just used to emphasize this type of collision, even though it's not necessary. So an elastic collision and a perfectly elastic collision, they're the exact same thing. You don't need the word perfectly there. It's just sometimes put there for emphasis. Now that's different from an inelastic collision, because when we talk about an inelastic collision versus a perfectly inelastic collision, they are 2 different things. So an inelastic collision is one in which the kinetic energy is not conserved. i.e., or in other words, Ki is not equal to Kf for that second blank. And then a perfectly inelastic collision. Now this is just a subcategory of the inelastic collision. This is a special type of inelastic collision, is one in which the objects stick together. Just like in the example we did on the front of the page with the 3 cases of the car and the truck locking bumpers, all 3 of those were considered perfectly inelastic collisions, because in all 3 cases, the bumpers, because the 2 items stuck together after the collision. And the maximum kinetic energy is lost. So I already know that kinetic energy is not conserved in an inelastic collision, but in this particular type of inelastic collision, it's the worst possible scenario where the most possible amount is lost. And for this type of collision, the kinetic energy is either lost, as some of it is converted into sound and thermal energy, or gained, because you could have an increase in the kinetic energy, or gained due to work being done on the system, or potential energy being released to the system. Like, for example, if two carts collide and there's a spring between them that gets released right at the time of collision, that's going to end up releasing potential energy into the system. So, let's look at this final example. This is an example where you have to cut it to solve something about the collision, and then to identify if it's elastic or inelastic. So an 80-gram bullet is fired horizontally with a speed of 350 meters per second into a block of wood resting on a horizontal frictionless surface, and the bullet exits the other side of the block moving at 150 meters per second. So the first thing we can note is that the bullet and the block did not stick together. If the bullet had become embedded in the block and didn't pass out the other side, and they were stuck together, then you could automatically identify it as an inelastic collision because it's perfectly inelastic, because the objects stuck together. Since the objects did not stick together, we cannot just, that doesn't mean it's now definitely an elastic collision. That means it could be either elastic or inelastic, depending on whether or not the kinetic energy is conserved. So we'll have to solve for something about it first. So let's do part A. What's the speed of the block immediately after the impact? So I'll move it over here. So with conservation of momentum, we're going to have M1 V1 initial plus M2 V2 initial equals, now because the two objects are not stuck together, I'm going to use M1 V1 final plus M2 V2 final. Since we're going to call M1 the bullet and M2 will be the wood, and since the block of wood was initially at rest on the surface, we can now just say that V2 initial is 0. And we are solving for the speed of the block immediately after the impact, which is, we want to find V2 final, the term I'm circling right there. So let's bring this term over to this side of the equation. That'll give you M1 V1 initial minus M1 V1 final is equal to M2 V2 final. And if you want to, and I'm going to go ahead and do this, you can factor the M1 out. So you have M1 V1 initial minus V1 final. And we're going to divide both sides by M2. And that will give you, that will tell you what V2F is equal to. So M1, that was the mass of the bullet. Remember, bullets are given in grams. You usually got to convert them into kilograms. So it's 0.08 times V1 initial, which was 350, minus V1 final. When it came out the other side, it was moving in the same direction at a speed of 150. And this is all going to be divided by the mass of the block of wood. So we have 0.08 times 200, which is 16. And we want to divide that by the total mass, or the mass of the block, of 15. And that gives a final answer of 1.06 repeating meters per second. Alright, so that is part A, the speed of the block immediately after the impact. Now in part B, we want to indicate whether the collision is elastic or inelastic. And the only way to do this is to calculate the total kinetic energy before the collision and the total kinetic energy after the collision, and then just see if it's the same or not. So K initial, the total kinetic energy before the collision, is 1/2 m1 v1 initial squared. That's for the bullet, plus, and technically I don't even need to write this part, the block wasn't moving, the block was resting, so the initial kinetic energy of the block is 0. So for the bullet, it's just going to be 1/2 times 0.08 times 350 squared, which is the initial velocity of the block, and that gives you an answer of 4,900 joules. So that's your K initial. The K final, well, now both objects are moving, so we have 1/2 m1 v1 final squared for the bullet, plus 1/2 m2 v2 final squared for the block. So we'll plug in 1/2 times 0.08 times the final velocity of the bullet, which was 150 squared, plus the kinetic energy of the block, which is 1/2 times 15 times 1.06 repeating squared. So when I type all this in the calculator, for the bullet, I get, looks like 900 joules, plus for the block, looks like pretty low, just looks like about 8.5 joules. So it looks like I get a final answer of 908.5 joules. So in that case, the initial kinetic energy is definitely not equal to the final kinetic energy. So we can say that this collision is inelastic. And the justification of the answer, we've already done that with the calculations. Okay, that is it for all the notes on conservation of momentum.